Hi everyone, and thank you very much for your interest and for coming here. So this is a very recent work that we completed few months back in Cambridge. We'll put this up on archive. So this talks about single file diffusion and the role that initial conditions play in determining the late time dynamical fluctuations. So this was carried out in collaboration with Mike and Rob, both of whom are from the same department, where I'm a postdoc now. So the statement of the problem is basically that transient behavior of a wide class of complex diffusive systems under certain geometrical constraints show an everlasting dependence on initial conditions. That once you specify an initial state, the system never really forgets about the initial state. It always holds on to the memory. Now, what kind of complexity are we talking about here? So we have an interacting many-body system, and the constraint that we are talking about here is basically the particles undergo single-file motion. So what is single-file motion? You have particles distributed either on a lattice or on or on the continuum, one-dimensional line. No particles are allowed to overtake each other. They're doing some kind of dynamics on their own. It could be on a lattice or on a continuum, as I said, but the position of one particle is really tied to the number of particles it comes in contact with in a certain amount of time. So this model is particularly interesting because it shows anomalous diffusion, which is different from normal diffusivity, and it has a lot of applications in industries, as well as it shows up in various kinds of natural processes. So, for example, one major source of this single file phenomenology are these zeolites, which are essentially mineral rich compounds that you find inside rocks. So if you look into the structure of these zeolites, you find that these are microporous structures with multiple shapes of pores, shapes and sizes of pores. So when you put these zeolites, say, in water or in some other kind of solvent, they allow for certain sizes of molecules to pass through while blocking the rest. Now, this has been a subject of interest for the industry for the last 70, 80 years. But very recently, this has really led to a boom in the chemical engineering sciences, where people have started to construct artificial zeolites motivated by the phenomenology of these naturally occurring compounds. So what they do is they take some kind of aluminum, silicon, and compounds and make these composite structures where you can see that there are these multiple pores. So these pores are usually of the order of, say, some nanometers or some angstrom. So when a particle of size larger than these pores try to go through, they are essentially blocked by these structures, and particles which are smaller than this go through. So they have a huge application in terms of adsorption processes in the industries. Another relevant application for this kind of single file motion or something that will be applicable in the future are these carbon nanotubes, where this is a schematic diagram of carbon nanotubes and how it allows water to flow in single file motion through the nanotubes. So these hexagonal structures essentially represent carbon, and these red and gray atoms are basically water molecules. So when water comes in contact with the carbon nanotube, because of the interaction between water and carbon, the water molecules are stretched, and then the water molecules are held together by hydrogen bonds, and then they perform single file motion. Because inside the nanotube, you only have a space of around a few angstroms for the waters to move, and the water molecules are themselves of the order of few angstroms. So they cannot really overtake each other. They perform some kind of single file dynamics. Apart from this, historically, the first problem where single file motion was first talked about was basically movement of potassium ions in biological membranes, the work by Hodgkin and Kynes. And also there are recent applications which talk about delivering protein-rich drug to particular places through use of cylindrical nanochannels. So in all these, the physical problem that we are considering is essentially this, where you have, say, an infinite line, and you have placed particles on the line, and say you have placed them with some homogeneous density, say rho bar, and you are interested in essentially finding out the displacement of one of the particles. So the idea is this: this is a fully interacting system, and you want to understand complex features of this system. And the way to do it, one way to do it, is essentially just tag one particle. Like for example, here you say you have colored one particle, and you follow the statistics of that single particle. So the idea is to follow the statistics of a single particle and infer information about the entire system as a whole. So, the quantity of interest, one major quantity of interest in these kind of systems is the mean square displacement of this tagged particle or a probe particle or tracer. There are various names. So when you study the tagged particle motion, you see that the mean square displacement, which I'm calling as variance of x of t, x being the displacement, the mean square displacement scales as square root t. So if you had a simple normal Brownian particle, then you would have a mean square displacement that would scale as t. This is the anomalous behavior that has created a lot of interest for a long time, and this is the subject of this talk essentially. Now, this problem, if you look into literature, this actually has acquired a status of a paradigmatic problem ever since 1965, which is the first theoretical work on these systems, at least to my knowledge. Nearly every 10 years, there has been one major contribution in the field, and the very recent being this review of Taloni, which really incorporates all this work into one particular review article. And so basically, the whole idea is we're trying to understand this single file motion, but there is a particular feature that we want to understand, and that is what makes initial conditions important in the phenomenology of single file motion. So in some sense, the birth of this problem goes back to Derrida and Gerstenfeld, but they are looking at a different problem. They're not studying single file motion, not studying mean square displacement of a tagged particle, but they're rather studying the distribution of current when you actually place particles at different densities on either side of an origin. So what is the problem? So they have what they've done is they have placed particles uniformly at different homogeneous densities on both sides of the origin. By uniformly, I mean they have taken particles. They've chosen the initial position of the particles from a uniform random distribution. So essentially, we're trying to understand problems in the thermodynamic limit. So we go to the limit n and L both going to infinity, such that my density n over L is held fixed. So note that there are two densities, rho left and rho right. And so this is essentially the description of the problem. And what they're trying to understand in this problem is essentially the flux of particles that goes from left to the right, because you have created a chemical potential difference because of these two different densities, and you want to understand what is the time integrated flux to the origin. So in this problem, there is a noted that there are two sources of randomness. One that comes from the dynamics of the particles themselves, because they perform some kind of random diffusive motion. And the other, interestingly, comes from the initial preparation. That is how you have prepared the initial state. So what do we mean by that? So, okay. And this Q is itself a random quantity because it has these random sources in it. And so the idea is how we handle the initial state determines the probability distribution of this time integrated flux Q. So what do we mean by handling the initial condition? So they prescribe two different methods. One, where you place the particles uniformly at the beginning, then whatever you have done, that is the initial profile. For every other realization, you just play around with the noise. You do not really tamper with the initial profile anymore. So this is called quenching, and this name quenching and annealing, these have been taken from the study of disordered systems. By quenching, we mean something that is frozen in time. So I have fixed the initial state, and that's it. So I am now changing my noise, and I'm seeing what happens for different realizations of the noise, but I'm not changing my initial state. The other, interestingly, is when you let the initial state fluctuate for every realization, and then you average over both the noise as well as the initial state. Now, there is something particularly quite interesting here, that the way they chose their initial state is through a uniform random distribution. And this is an important point in the rest of the talk. So with these two different ways of averaging, what did they see? in these classes of problems of current, they saw that there is an everlasting memory of initial conditions. First of all, when you look at both these annealed and quenched settings, at the level of the mean, they both give the same result. There is no difference. However, the moment you look at the second moment, you get to see different results. What kind of results do you see? They also calculate the large deviation results for this problem, and they show that all moments actually scale with time as square root t. So that scaling is out of the question now. The only interesting thing that you have in this problem is the coefficient of subdiffusion. Yeah.
First of all, talking about a stationary state with a periodic boundary condition.
No, no. So it's an infinite system.
Is that for a given initial condition, are the computation a long time depend on the initial condition?
No. If you have given an initial condition and fixed it, then the initial condition has no fluctuations in it. That is the subject matter of the talk. If you have fixed the initial condition, then you'll only get one particular result, which is the noise averaged result. So that is essentially their quenching scenario. So what did they observe? So in the case of annealed and quenched, they saw that both of these results. When you look at the variance of the current, the second moment, the second Q moment, they saw that the variance gets a square root t. However, the annealed and the quenched results differ by a factor of square root 2. Now, initially, the first problem that they looked at, they used hardcore Brownian particles, and then they studied non-interacting Brownian particles, and eventually they solved a full hydrodynamic theory which encompasses a lot of different macroscopic processes, for example, simple exclusion process or hardcore Brownian particles or random average processes, and they showed that for all these different macroscopic processes, there is one hydrodynamic theory with which you will actually get the same result. If you take the annealed initial condition where you let the system fluctuate, or you do not let the initial state fluctuate, then you will see that annealed and the quenched results are different by a factor of square root 2. So once Derrida came up with this problem, people are very quick to realize that you can actually borrow the insight from this problem of current to the problem of a single file diffusion and tracer motion within a single file system. So this is the problem that we are really interested in. And what did people see immediately after Derrida's work? So Derrida's work was in 2009, and then starting from 2010, people started to see the same kind of effects in the motion of a tracer particle in this infinite infinite single file systems. So at least what I believe the most important contribution in this field came from Kavitsky, Mullik, and Sadhu in a PRL that they wrote in 2014. But they again used hydrodynamic theory because the works before these people were actually taking particular examples of macroscopic processes and calculating mean square displacement. But what these guys showed was again that you can use this macroscopic fluctuation theory, which is a hydrodynamic theory, and take this binary way of looking at things as annealed and quenched. And what you get is again that even in the case of a tracer, the variance of its displacement or the mean square displacement in the annealed case and the quenched case, they differ by a factor of square root 2. Then you start to ask, if you don't, after this result was published, the last 6-7 years has seen a lot of work on these kind of single file problems. And whenever you look at single file problems, a kind of binary has been established that you have either this annealed state where you let the initial state fluctuate with this uniform distribution, or you start with this quenched state where you have fixed the initial state and then waited for a long enough time and just average over the noise. But then you ask that is this kind of stationarity important? In sense of stationarity, I mean when I'm choosing an equilibrium like dynamics, this is some kind of a stationarity, although in an infinite system there is no reason to expect stationarity. And the other is when I've fixed the initial condition, there is nothing changing with every realization. But the answer to this question is actually hiding in the details of the system itself. Because if you look at the numerical studies of the quenched state,
this is only true for subdiffusion, is it? Because I could imagine the same thing for a diffusion. where I have started with a quench T. Suppose I really expect a diffusive behavior in the long time living for a that means square displacement. And I start with a quenched initial configuration, only average over the trajectories, or I start with I average over initial condition as well as. There is no factor of √2 that has been reported for that.
No.
Only for substitution.
Yeah, because I mean, as we'll see, because I mean, the density fluctuations actually affect the subdiffusive behavior itself in a very linear manner.
And by subdiffusion, do you mean precisely √T or anything slower than?
Okay. By subdiffusion, I would mean anything slower than T, but for the context of this problem, I mean square root. Because there could be various kinds of subdiffusive behavior depending on the waiting time that you give, continuous time random walk, and various other things. So you can have various kinds of problems in this set of problems in this class of systems.
But √2 has not been established for any of them.
No, as far as I am aware, no. I haven't seen any other model which is not just this shape-like models or simple expression process-like models where I've never seen any studies on those processes where you have a square root 2 coming in. But okay, I'll end with something. I'll show that there is another system where you can see a square root 2 as well. So the point is, if you look into the literature, then you see the way the people have studied numerical structures of or numerical way the way people have studied numerically the quenching effect is to putting the particles in an equispaced manner. Now, this is quite odd because when you define the quenching protocol, there is no mention of any equispacing. You just say that I will throw particles uniformly, and I will wait for a long time and I will change the noise. I'll change the noise at every realization. But I don't really mention that I'm putting my particles in an equispaced manner. Because even if you don't put particles in an equispaced manner, if you wait sufficiently long time, then you'll still get the quenched result. But if you look at the literature, you see that okay, this is not working. Okay. So if you look at the literature, then you see that people have placed particles in an equispaced manner. Now there are microscopic theories which can show that if you start from an equispaced manner, then if you write down the moment generating function, it will converge on the quenched moment generating function that you already have. But that is not the reason for really starting with an equispaced manner. I mean, you could have started with any other configuration of the initial state. So, but you note something that when you equispace particles, that really minimizes the density fluctuations. Because if you have placed particles in an equispaced manner, what is the fluctuation? There is no fluctuation anymore. So this begs the question, is there a correspondence between density fluctuations of the initial state and the fluctuations of the dynamical observables? Now this is particularly important because the density fluctuations of the initial state are talking about fluctuations in space at time t equal to 0, and the quantities of interest that we have are dynamical observables. We are measuring x square as a function of time at late time. This is really relating space with time, and we are trying to understand if there is a correspondence, and if there is indeed a correspondence, can we quantify this correspondence? That is the central question of this work. So before we go into the work, so let's look at what people have studied so far. So when you choose your initial state from a fully uniform distribution, then it is equivalent to saying that there are no correlations in the particle position. But when you and for this kind of initial states, what really holds is the fluctuation dissipation relation. Now, if you place your particles in an equispaced initial condition, then your particle positions are maximally correlated. Because if I know the position of the first particle, then I can tell you what the position of the final particle is. So what we want to do is now come up with a unifying mechanism that incorporates both these annealed and quenched results and also these equispaced and these fully fluctuating initial conditions. So that is the question. Is there a unifying mechanism? Yeah.
So how can when you place it in equispaced manner, then you say the correlation is maximized, right? So how how the density fluctuation is minimized?
Because
the fluctuation is
so there are two things. One is the fluctuations in the number of particles in a region, which is essentially your density fluctuations, and the other is the correlation in the position of the particles. So it's just the inverse.
fluctuation is the integral state
Yeah, but what I'm talking about, when I say that particle positions are maximally correlated, understand in this manner that if I fix the position of the first particle, then I've essentially fixed the position of the last particle, because each particle will just be equispaced from its neighbors. That is not the same as density fluctuations. Density fluctuations
is deterministic, right?
equispace is deterministic. Yeah.
But it doesn't have to be equispace. Deterministic and
Yeah, points could be anything that is deterministic. Yeah, it could be, and even if you can show it in a random manner, if you don't really let it fluctuate, it will still be quenched. So, is it clear? So what we'll do is we take out this quench business. We don't quench anything. We are going to carry out an annealing procedure, but we're going to introduce a twist in this. What we do is we allow the initial states to fluctuate now, but we take out the constraint that is imposed by this equilibrium fluctuation dissipation relation. That is the only input that we are providing in this problem. And then we average over all allowed initial configurations. Allowed is important here, because we'll see that we are going to introduce a measure of density correlation in the problem. And so whenever next, from next slide onwards, whenever you see this quantity variance appear, note that it is averaged over both the dynamics as well as the initial configurations from now on. So I'll just give you the main results first before getting into how we arrive at the results. So the result, the first main result is essentially this. If you look at the mean square displacement of a tracer in this homogeneous interacting system, then you can actually break the mean square displacement into two parts. One that comes purely from the noise and has no information about the fluctuations of the initial state, the density fluctuations of the initial state, and a separate contribution which actually encodes information about the initial density fluctuations. And how does it hold the information? Entire information about the initial density fluctuations can be captured by a single number. It's a static quantity, and I have denoted it by alpha IC. IC stands for initial condition. What is alpha? Alpha is an asymptotic variance. You find this alpha a lot in the studies of hyperuniform literature. So this alpha is essentially, it is a name, which is a generalized compressibility. The name is essentially a Fano factor, and this Fano factor is associated only with the initial state. Now, if your initial state is an equilibrium initial state, where you have just thrown particles uniformly, then your alpha IC coincides with the compressibility factor. In any other case, it's a Fano factor, it's a generalized compressibility. And we'll see that this is basically, this is the result. I mean, it is this alpha IC that really controls subdiffusion.
Why do you call it equilibrium? It's just a static thing, right?
Yeah, I mean, this is the, I think it's a problem of the literature. People have been calling it equilibrium, although there is no reason to expect equilibrium. It's just people say that, okay, I am assuming that my system has reached equilibrium, and then I start measuring my, or you can say I can start from, say, in equispace condition or whatever condition. I've let it equilibrate for a long time. That is, I've run the system for an infinite time, and then I've started measuring. Then the system will just keep seeing an equilibrated system. So, but there is no boundary, so there is no reason to expect equilibrium. But it's a fallacy of the, or whatever. It's a thing that goes on in the literature.
So maybe I missed it. What is NL?
Oh yes, right. So NL measures the number of particles within a certain distance L from your point of observation. So this alpha IC is essentially a ratio of the variance of this number NL over the average of this number.
The number of particles in a subsystem.
In a subsystem or in a certain region L. So L is a certain length scale that I'm going to draw. So you have a point of observation. It might be the tracer, or it might be the, for example, in the current, for the problem of the current, it could be the origin. So I have a point of observation, and from that point of observation, I'm saying there is a length scale to the problem that is of interest to me. So it is the number of particles within that length scale. So so this alpha IC essentially is a ratio of the variance of that number divided by variance to the mean.
And when you say variance, you mean you don't have quench initial.
No. This is now all about initial state. There is no fixing anymore. So I change my initial state every time. So this will produce. I'll show you in a moment. But alpha, what I mean by alpha.
Okay, I see. So you are saying that if alpha is, for example, 0
Mm-hmm.
or very small, then you have almost quenched it. And if you are well,
yes. Because alpha, if alpha is 1, then you have an ideal gas. Then you have the compressibility for ideal gas, compressibility factor for ideal gas, which is 1. So the interesting part is, if alpha is 0, what you have are hyperuniform initial states. This is by definition. But by hyperuniform, what I mean is clear. We will see clear in the next slide. So the point is, this is how hyperuniformity really comes into this problem. The most interesting result is, if you see that alpha, if alpha is 0, then your mean square displacement is always going to be just this part, the noise. The contribution from the noise will be the only contribution. But alpha IC can be 0 in a various possible ways, because alpha is like a macroscopic measure. So what I mean by alpha is, so let's visualize what alpha is. So here I'm showing you essentially 3 different values of alpha. I'll tell what the values of alpha are in a moment. So you see, as you go from top to bottom, so this is, the red is one value of alpha, the green is another value of alpha, and the blue is the third value of alpha. As I go from top to bottom, I see that for each realization, the fluctuation in the number of particles keeps changing. Fluctuations keep increasing. So what I have here is basically 40 particles in a region of length, say 100. So all of these correspond to a density of 0.4. So what are these? The first 3 correspond to alpha is equal to 0. If you look at the first line, this is the equispaced initial condition. In the second line and third line, I have just given a little bit of random displacement to the position of each particle. But
sorry,
yeah.
When you defined alpha, you said nothing about A. Do you have larger limit in mind?
Yes, alpha is always defined in the larger limit. So I will technically define alpha in a moment. I'm just visualizing what I mean by changing alpha. So now this first line is the equispaced line, and then if you just give order 1 random displacement, these are all still corresponding to alpha is equal to 0. Nothing is going to change in the system. Now these are okay. This is a random value of alpha that I have chosen, and for this you see that the fluctuations between each realization are much more compared to alpha is equal to 0. So you're really increasing the fluctuations in the initial state. That is what you are doing by changing alpha, and this is really an ideal gas situation. So this is what I mean by alpha, just to let you visualize, and then I will walk into the problem. So before really talking about this problem of single file diffusion and calculating the mean square displacement, which is quite a non-trivial task, I will first talk about, I'll take a detour through a non-interacting system where the physics or the physical mechanism will be clearer in a much through a much simpler analytical calculation. So the system that I'm going to study is this. So I'll place particles not uniformly. I'll place particles at a homogeneous density rho bar to the left of the origin. There will be no particles on the right. All the particles are going to be non-interacting. So there is a bunch of particles, but they are not really talking to each other. And for this step-like profile, I'm going to measure the variance of this current. So I will show you that it is the same physical mechanism that controls the current in this system as is the physical mechanism that controls pressure motion in a single file system, which is this one. So let us first look into this system and see what we get. So what is, as I said, so I have n particles which are pressing between 0 to minus L, n I will go to infinity. So I have a homogeneous density. I want to calculate the variance of this current, where this Q is essentially the time integrated flux. The question is, how do density fluctuations of the initial state affect this variance of Q at a late time t? Now, to study this problem, we had introduced a counting statistics way of really studying this problem years ago. So where you basically take this counting function chi. So if the particle I is to the left of the origin at time t, then you say that chi is 0. And if the particle is to the right, then you say chi is 1. So what this is doing is, this is converting a problem which is a time integrated problem into something that is instantaneous in time. Because when you're looking at flux to the origin and these particles have some kind of diffusive motion, I'll explain what the motion is. I've not talked about the dynamics. The point is, if a particle has come to the right hand side and has crossed over, so at time t, if it is already on this side, then it is not really contributing to the flux. So this is a method that we had used when it allows you to understand things in a very simple manner. So if you want to fix, so now for a given initial configuration, if you want to calculate the current, then this current is just a sum over this counting function chi. Right? goodness. Okay. So if I'm so now I have two sources of randomness. So one is the randomness that comes from the noise. So if I look at the noise average value of the flux, so this is just the average over averaging basically the chi i's. And what is the average? So since I have non-interacting particles, I can define the average in terms of a single particle propagator. Because this G is essentially the propagator, it tells you the probability density if a particle starts from some point y at time t equal to 0, that it has reached x at time t equal to t. So this function u is essentially the integral of the propagator. So now we want to calculate the variance, and I mean the variance of q. So what we have to convert this, it's better to convert this summation into an integral. And okay, the dynamics that we're going to talk about is essentially Brownian dynamics. So in the late time limit, all particles, so this is the only dynamics that we're considering. All particles have Brownian dynamics. So if you plug in the Gaussian propagator in this expression, so you will get basically a complementary error function. Now we have to convert this summation into integrals so that the calculations become much easier. So for that, we introduce this empirical density rho. This rho is nothing but a sum over all delta functions which measures where each particle is at time t equal to 0. And this is again for the initial state. So now I want to measure what my variance of qt is. And so basically, what is the variance? We just take the total variance of q when averaged over the noise as well as the initial configuration. So you have to be careful about where you put the square and the angular brackets here, because that is what simplifies the problem. So here, these angular brackets will represent noise average, and the over line will represent average over initial conditions. Essentially, I have this is the quantity that I want to calculate. So now, in this kind of broken algorithmic problems, there is a trick that was shown by Palmer in his review of 1985 review, and also you can find this in the book by Goldenfeld. You just add and subtract n quantity. So what we're doing here is we're essentially adding and subtract noise average q square to this expression. So if you do that, the first two terms will give you something, and the next two terms will give you something else. What is this q square noise? So if you plug in all the expressions of u and g and all these things, you'll essentially get this result for q square noise. But what is this? This we see is already the quenched result that Derrida had obtained for his stepwise profile, and also what we had obtained. So this is telling you that I have not annealed the system, but I've already obtained the quenched result within this annealing procedure. So something else is hiding in this problem, but I can actually obtain whatever I obtain by quenching by an annealing process itself. So what is this q square I see? So if you plug in again the expressions, then you'll see that all the density fluctuations, all the information about the initial density fluctuations hide through this this quantity, which is essentially the covariance of the density in q square IC, delta q square IC. So this is the quantity that we want to calculate. So how do we handle this particular guy? This is now, because this is where the interactions are, not in terms of dynamics, but in terms of the initial state. So what we assume here is basically a translation invariant system. So we said, since I had particles from the left of the origin, I said my system is really infinitely extended, and then I chop off half the system. So this is how I put in the theta functions here. These are the Heaviside theta functions, and this C of Z1 as Z prime is essentially telling you that now, since it's a translationally invariant system, the dependence on Z and Z prime is only through the difference between Z and Z prime. So then I define the Fourier transform of this quantity, which is also called the structure factor. And if I do that, then I can write my q square IC in terms of the structure factor in this form. I have just put in all the values of u and everything. But note, we are only interested in the large time limit. So in the large time limit, the argument of S that is going to dominate Q square IC is essentially S of 0. But by definition, because see, T goes to infinity, so it is dominated by S of 0. But by definition, the limiting value of this structure factor is alpha IC. This is the definition of alpha IC in terms of the density fluctuations of the initial state. So this is to answer your question. So Q going to 0 is essentially L going to infinity. So I'm really looking at a large length scale property. And you can see that if S of Q goes to 0, then alpha IC is 0. And that is the definition of my hyperuniform. So essentially, if I now take this thing out, then I can write my Q square IC as alpha IC times something else, which is essentially square root 2 minus 1 times the Q square of the noise contribution itself. And this gives me this result for the current, that there is a contribution from the noise and there is a contribution which encapsulates the full dependence on the initial fluctuations in this quantity alpha. So what does this mean? That the long wavelength density fluctuations are the only source of this everlasting memory in this class of initial condition dependent one-dimensional diffusive systems. So, okay, I'm just skipping over a few. If you're interested, I'll talk about how to macroscopically generate these values of alpha. I can talk about this later on. I'll just show you the numerical results now. So, on the left, I just use passive Brownian particles, and I measure var qt as a function of time. So, what I see here is, so each of these lines are my analytical predictions as a function of alpha, and the points are essentially the numerical results. So, I see that the agreement is quite good, and on top of that, so as I said that alpha is equal to 0 is a hyperuniform state. So I study two different configurations. One is equispaced, which gives me this previous points result or hyperuniform result, as I call it now, or if I can choose a randomized hyperuniform state where I start from an equispaced initial condition, give some order 1 fluctuation, and then I measure the current at the late time limit, and I see that they also agree at the same time. So it is telling you that it is really alpha IC, the large length scale property of the system, at time t equal to 0, that determines what is the dynamical fluctuation of the current at a very late time t. On the right, I have just taken a few examples of active particles. I mean, this is just to really see how concrete these results are. So microscopically, this is, I've taken the Nanotubes process or active Weinstein-Wilhelmsberg or active Brownian, everything in one dimension. None of them are interacting with their neighbors or anyone. All these models, they have been shown to follow late time Gaussian behavior. So you expect all of them to also behave in the same manner, and that's what they do. So we take just two different values of alpha, and we see that even for all these classes, we get the same result. So now, let us look at what the physical meaning of this result is. What is alpha really doing? So this U Z T, which is the integration over the propagator, is essentially, because we have taken Brownian dynamics, it has a length scale associated with it, which is essentially the square root 4 dt. And this is that L that you had initially asked about. If I look at the noise average flux for a given initial profile, if I look at the noise average flux, you see that this is determined by UZT. That means it is this length scale that is determining the noise average flux. Q square IC is nothing but the variance of this quantity. See, this is just Q square average minus Q average square. So this means that the noise average flux is controlled by the number of particles within square root 4 dt of the origin, because this is the length scale which is being set by this propagator, and it is the variance of this number that alpha IC controls, and in turn determines Q square IC, and that's how the fluctuation in a certain length scale initially determines the value of the current in a very late time limit. Now, having this insight with us, now we'll move to the interacting problem. So to study this interacting problem, we're going to use macroscopic fluctuation theory. So this is a hydrodynamic theory which encompasses a lot of microscopic interacting processes. Some examples are simple exclusion process, where particles live on a lattice. They can hop to their neighboring site if the site is empty. If there is another particle sitting there, that hopping move is not allowed. Then you can have particles in a continuum, but they cannot cross each other. Yeah.
I don't think can you go back to the
Yep.
mention that alpha IC determines the fluctuation within a 4BT bit, right? From the so suppose I engineer something where it really changes.
Alpha IC,
Homogeneous.
no. Alpha IC determines the fluctuations for the entire system. The system only sees in time t a distance which is of the order square root 40.
Yes.
Yeah.
So that's what my question is. Suppose it so happens that I calculate one alpha IC for a certain time. I mean, since the system doesn't see it anyway, suppose I only calculate eta L or ML or L is just 240.
Yeah.
Okay.
Yeah.
And then for certain time t, I can get some value.
Mhm.
And then the value changes, then I actually am increasing my range.
No.
That is possible. I can engineer some.
Oh yeah. Okay. Yeah. Of course. So you can say you start from a fully equispaced initial condition, but you don't start measuring your system. You let it equilibrate. The particles do their own Brownian dynamics, and you start measuring the these quantities after some time t. So you have really changed the initial configuration at the beginning.
No, other way around. I would say that suppose initially I start with a pretty equidistant thing.
Yeah.
Till
Okay.
some distance.
Yeah.
And then maybe I randomize a bit. Which means that for short time,
Yeah.
when the system sees only till a certain length scale,
Yeah.
it effectively sees one value of alpha.
Yes.
And then at longer times, it changes.
No. So no. So the point is, so it's the other way around. So if you wait a certain amount of time, say a finite amount of time, before you start making your observation, then the system will start measuring this annealed state, because system will have equilibrated in that amount of time. But if you have say for example, you have let the system equilibrate for some time t equal to 10, whatever the unit is. So now you start measuring after t equal to 10. You start measuring for the first t equal to 10 in the measurement window. You will measure the annealed result, because around the tracer, the system has equilibrated. But after that, it will go over to what is the original Fano factor of the system. So if you had started with a certain Fano factor, if you had chosen a particular alpha, waited a finite amount of time, for time scales beyond that finite waiting time, you'll actually keep measuring whatever the Fano, because the changes in Fano factor in these diffusive systems, they take infinite time to actually relax. So whatever is the Fano factor remains the Fano factor.
Actually, be the global alpha, I think, not
Yes.
the local.
Yeah.
No, I think I got it wrong. NL, I thought that L is actually.
No.
It is
So
changing.
that NL is actually the square root quantity, because the system can
No,
scan.
then again, then again, you are saying the same thing. If that L is scaling as for BT.
Okay, I see your point. Okay. So that
I
is
was
because
wondering that is it possible? Just to, I mean, my final question is it possible that I am measuring means my displacement,
Mhm.
but at different time regimes, I am actually getting results for different alpha IC because the fluctuations are changing.
yeah, whatever. Yeah. You can have that, but you cannot have the. I mean, so the point is, if you have defined an infinite system with a particular alpha, the system will eventually, the long time limit will measure that alpha.
The
But
global one.
the global one, yes. But locally, initially, for small time limit, it will measure whatever alpha it sees around itself. When I said that L, that was to just, okay, that's a notation. That is to see that, or say that if I start, for example, I'll show you in a moment what that L really means, and the square root 4dt really means, because in a diffusive system, that is a natural length scale. So in time t, the system can only scan up to a certain. But if you had started off, say you had started off with some Fano factor and let it evolve for some square root t time,
So
or
this 4DT also scales with time.
yes, so it will keep on growing.
With time, right? So then actually it is longer and longer.
Length scale.
That can, point was that can change the value of alpha IC. And then how does it reflect in my?
No, so alpha is essentially the variance over the mean. So the mean always goes as x in one dimension, but the variance, that is determined by whatever, how you chose it. I didn't show you how to really make these alpha IC states. So you have actually, when you, numerically at least when you prepare a system, you will see that there is a particular natural scaling that you introduce in the system when you specify an alpha. So that is a property of the large length scale. So I mean, the answer is yeah. The answer is whatever the fan factor is, the system will measure that in the large time limit. Okay. So the single file problem that I want to study is this. The way I want to study the single file system is through this macroscopic propulsion theory, which is a hydrodynamic theory, which takes into account a lot of different macroscopic processes. So what is meant by macroscopic fluctuation theory is that it doesn't look at individual particles anymore. It looks at a coarse-grained value of the coarse-grained density. So it's a macroscopic density field and looks at fluctuations of this coarse-grained density field. So what is this theory? I mean, so I'm not going into the technical details. It's just that this is the Euler-Lagrange equation that is the theory itself. So I have a fluctuating density field rho, which is given by this equation, where this d and sigma are two transport coefficients, and this eta is a Gaussian white noise. So there are explicit calculations from various microscopic processes which derive this equation. These quantities d and sigma, with the two transport coefficients, which are, if you know d and sigma, essentially you know the theory. So these two things are not arbitrary; they are related by the fluctuation dissipation theorem in equilibrium, where this quantity f is the free energy per unit length. So this is the theory that I'm going to employ to do what? So I want to calculate the mean square displacement of a tracer particle in a single phase system as a function of the initial state. That is the problem that we are addressing using this theory. So I'll just quickly go through these things. So what you have to do in this problem is essentially define the action, because we want to solve the moment generating function in this problem. So we essentially define the action. So what do we have? So my variable here is x, which is the position of the tracer at time t. T is some late time, and I have a formalism for this. This is the Martin-Cigliaro's formalism. This was pioneered in this context by these two guys, Paul Krivitsky, Yormoli, and Philip Sadhu. So what you do is, so this is the action that you have. So this lambda is a Lagrange multiplier, and you have this x. F is essentially the log. This f term represents the log probability of the initial state, which actually holds any information about the density fluctuations of the initial state. And you have a Lagrangian part, which is essentially coming from the dynamics. Here, this rho hat is a response field that you introduce in this Martin-Cigliaro's formalism to define Dirac delta functional. So these are technical things, but the whole point is this is the action which I have to minimize and obtain the density field that really minimizes the action, and it is that density field that we are going to use to calculate the variance of the position of the tracer. This is the whole, like, the clock of this is the calculation basically. So in this problem, you also need to have a physical constraint that will give you the boundary condition of the problem. This is really an initial condition, but it's a term because you use partial differential equations. If you say this is a boundary condition, this is really an initial condition, but this has to come from a constraint, and the constraint is this hardcore constraint that the tracer conserves the total number of particles at all times on either of its sides, because the particles are not allowed to cross each other. So the only thing that you have to now understand is how does this alpha IC enter the problem for this interacting homogeneous system. So what we are going to do is we're going to take this large T limit, then do a saddle point calculation to compute an instanton. These are just names. Instanton here is the solution that minimizes the action. So that is what the instanton is. And this is the density field that we are after. This is the instanton, essentially, it's a name. So we need the instanton that generates a large value of xt, and that large value will be parameterized by the values of the Lagrange multiplier lambda. So since we only want results of the order of the variance, it is enough to compute things at the order lambda square. Yeah.
So we have to calculate large deviation.
We have to calculate large deviation function, but the typical we will just only concentrate only up to the typical fluctuations. So not really go into the full large deviation problem. So that is what this is. We only want to calculate up to order lambda square. So what you have to do is we just do a perturbation thing now. So we expand rho around its homogeneous average value in order lambda. So this is the first order perturbation. Q1 is the first order perturbation to the density field, and this rho hat doesn't really have a zeroth order lambda correction because or a contribution, because if it contributes at order lambda equal to 0, then you have something which is unphysical, because the system with this rho hat is a response field. You cannot have a response field at time equal to 0. So anyway, we need this quantity Q1 and P1. That is what we have to solve. I will not show any of these technical results. The point is, the way alpha IC enters this initial profile is when you just expand the free energy in terms of the density to quadratic order. If you do that, then you will see that essentially, so see, this is essentially the action. So action is e to the power, then the way you have to handle the system is e to the power minus s. So this is essentially telling you, as long as your density fluctuations are Gaussian, the variance is controlled by alpha IC. This is how alpha IC really comes into this problem. Because what I have done here is essentially, so this capital F is just integral over x small f. Small f is essentially the free energy per unit length, and this is the integrated free energy. So you expand this f of rho around rho bar to quadratic order, and then you essentially get this. And alpha IC again is by definition the compressibility factor. So this is how alpha IC enters the problem. So once you have done this, all you have to do is extremize the action or minimize the action to obtain the dynamics of Q1, and you need a boundary condition. So that boundary condition will determine the tracer's fluctuation, and the boundary condition essentially is this one. So I have Q1 at time t equal to 0, which is telling you to the first order. So what is Q1? Let me just go back. So Q1 is the order 1 fluctuation of the density. So you need this at time t equal to 0. The idea is, so if I know the initial density fluctuations, then I know at time capital T, because this is already sitting here, because it's a backward, you calculate this for a backward propagator. So if I know this quantity Q1 x0, then I know where my tracer will land up. So if I plot Q1 of x0, this is what I see. So you see, alpha controls the strength of this perturbation. If alpha is 0, then you have this fully equispace, fully hyperuniform or homogeneous profile. If you now increase the value of alpha, then you see that this is a time t equal to 0. This is telling you that there is a pileup of particles on one side of the tracer and a dearth of particles on the other side. Now note that this is a problem that has symmetry. So whenever you do the calculations, what enters the calculations are basically values that are like Q1 x0 square. You cannot end up with a term which is Q1 x0, because that will bias the tracer. But this is also telling you that if you have a pileup on the right of the tracer, on the left of the tracer, then that fluctuating density profile will bias the tracer to the right, and vice versa. So this is all that you need, and once you use this, you essentially get to this result, where once again you can break the mean square displacement into a term that comes solely from the noise fluctuations or the noise, and there's another contribution where alpha sits in exactly the same manner as it sat in the current problem. And what do I have? So this noise contribution in terms of the transport coefficients, d and sigma, is essentially this. And if I look at the other this quantity x squared dense, so the density, this essentially these are the two results. Now I want to test this hydrodynamic theory through a macroscopic model. So I know what the values of d and sigma are, say for hardcore point Brownian particles. So for these particles, d of rho bar is essentially d. D is the diffusivity of a single particle, and sigma of rho bar is 2d rho bar. Usually, if you look into the literature, they essentially drop this d and they just write d of rho is 1 and sigma of rho bar is 2 rho bar. But if you are consistent, then this d appears, and then you can write this mean square displacement in case of hardcore point Brownian particles in this manner. And this is what the simulations are telling you now. So this is the left hand side is telling you Q1 x0, is giving you Q1 x0. So you change alpha, and you see go from the hyperuniform state to the fully disordered constant state. And we are essentially measuring two different kinds of hyperuniform states. And yeah, agreements are quite good. And what you see here is, if you look into this Q1X0 profile, you see that the length scale that really matters to the tracer is essentially square root 4 dt, because you see this function, or the Q1X0 that I showed. Go back. So this function is essentially telling you how much a complementary error function deviates from the step function. So this is the natural length scale, this square root 4 dt. At around 1, this kind of drops off. So now, just to give you the link between this interacting single file motion and this current of non-interacting Brownian particles. So the link is essentially, in technical terms, this is called interchangeable world lines. So what really matters at the hydrodynamic scale are the number of particles, or the density, not the individual particles. So for example, this is not the best picture, but just stay with me. So here, say I have 3 different particles, red, black, and green. So in this case, the particles are hardcore. So when these 2 particles come, they reflect off each other and they maintain their initial order. In this case, the particles, the 3 particles, they are going through each other. So at the level of a single particle, if I just look at a black particle, so this is its position here. But in this picture, it is freely diffusing, so it can move to a different position. So at the level of single particles, these 2 pictures are different, but at the level of density, they are the same. And that is why, that's why we took this detour of measuring this current problem, where what really matters is the bunch of particles around the origin. If you understand the physical mechanism that causes the current to flow, you understand the physical mechanism that creates this boundary layer for the tracer. So just to summarize, so the main point is, dynamical fluctuations in single file diffusive systems are controlled by the Fano factor alpha IC. This binary way of looking at these single file systems through annealed and quenched, this is an incomplete picture. The complete picture is provided by alpha. What is this alpha IC? It is just a limiting structure factor. It is a property of large length scales, and it remains unaffected by finite equilibration times. If you have hyperuniform states where alpha IC is 0, the consequence of having hyperuniform initial states is that you minimize the dynamical fluctuations, because they are giving you the quenched result, which is the lower line. And previous annealed results, which people had previously got, now you can show that they are just one member of an infinite family parameterized by alpha IC. Why? Because the previous annealed results are just the value of alpha IC that the system takes in its own stationary equilibrium state. If it's a system of point Brownian particles, then alpha IC is just 1 in the equilibrium state, and that is the previous annealed result. But we have a full spectrum that incorporates both the annealed and the quenched results. And of course, the non-interacting system and the current, you can generalize these results to higher dimensions. They will always hold, even for if you just define a surface or define a line and look at the flux to the surface of the line, those results will hold. So that's the summary, and yeah, this is the main point, the first line. And yeah. So, there are various possible extensions of this work. The first thing would be to look at large deviations of this problem, because now you have large deviations coming in from the density itself, from the initial density fluctuations, as well as from the dynamics. So these 2 can come together and give you completely new set of results. So you have to understand what the large deviation picture is. Then what happens when you have interacting active particles? So all the systems that I talked about so far have a microscopic reversibility. So when you break this reversibility at the micro scale, we expect things to change. So we would like to understand how that happens. Then you would like to go to higher dimensions and study what happens when you introduce shape to the particles. Because you have rod-like particles, then a lot of interesting things can happen. As well as, I mean, this is a much later future, we would like to understand what kind of applications these kind of single file systems or these kind of single file problems, theoretical problems, have in material science. So that is it. This is, yeah. Thank you.